Okay, so in this video, we're going to go through the phase lock loop, the basic concepts of what's going on. Here we have our four main components. Now, keep in mind that the divide by or programmable divider, it's not one of the criteria required for the phase locking portion, right? We only use this portion. This portion is only really used to get a synthesized frequency greater, right? So we use the divide by in order to increase the output of the VCO, right? So this is just for greater frequencies. If we don't want any greater frequencies, we can just use a feedback straight path into the comparator, right? But anyway, going through it, so first things first, our crystal controlled oscillator is just a normal oscillator, right? It could be a Colpitts oscillator, it could be any kind of oscillator. We'll see that in the KY92, it's an actual crystal combined with a divide by 2 to the power of 7 to get us a 25 kilohertz input signal. So let's just use that for argument's sake. 25 kilohertz is that signal. So let's start with the signal goes through a phase comparator, right? It could also be called a phase detector. The names are interchangeable. Some sheets will call it phase detector, some will call it phase comparator. From here, right, the output on this guy when it's comparing, so at some certain portions, this guy's phase, depending on what the signal looks like, this guy might be a little bit more ahead, right? So in other words, if we look at it from this perspective here, we have a sine wave, right? So if there's a sine wave coming on this one, and this guy here sees a sine wave, right? And say these sine waves have different peaks. So if we're talking about an op amp and just a straight up comparator, well, we have inputs that are, say, positive or negative, right? So when we look at it, you can see if they aren't in phase, there's going to be portions of this sine wave where he's going to be at his peak and he's not going to be at his peak. So if you just, and remember the way the comparator works is just whichever one's more positive. Okay, so that's how this error voltage is produced. And remember what's coming out, and then the same thing's going to happen later on, right? So as this guy's phase, his phase goes out, this guy comes back, he's at his peak where he's not. So then the signal, the output signal is going to look something, some sort of repetitive square wave, okay? So depending on how much they're in or out of phase will determine the duty cycle, how much time it spends positive, how much time it spends negative, okay? Now remember, this is flowing on a reference line, okay? So when we talk about reference line, we're talking about also the fact that if the duty cycle is not 50%, right? So if it's not 50 equal off as it is on, you can basically say that if it's a 50% duty cycle, that if say it was 5 volts, right? It's equal off as it is on, then you can just divide it by 2, right? Or sorry, not 2. Divided by you can divide just by 2, half it, right? So, and that would leave you with 2.5. So your average voltage would be 2.5. Anyways, so from here, so that square wave then goes into a low-pass filter. And this is where this charging, discharging a resistor capacitor is coming to play, because the capacitor is going to discharge and charge this guy, and he's going to keep, and what's going to happen with the discharging, charging, right? So he's going to charge, and then he's going to discharge. And we're going to select capacitor values that lead us to a very, flat out or almost DC level at this point. And that DC level just so happened to be riding somewhere in the average of how much time he is in on or off. Because if he's, say that's spread out more, right? So say this is thinner, but it's off more times. Well, you can imagine that the DC level is going to be a lot lower because the capacitor is going to have more time to discharge. You follow? So that's, at this point here, we have a DC. So for all intents and purposes, at this point, we have DC. Okay? So that DC value goes into a voltage-controlled oscillator. That DC value potential is what's going to change the varactor. So in the front of this voltage-controlled oscillator, remember, a voltage controlled oscillator has a potential. So this is the trigger, right? And it's got a varactor that's going to phase, right? So it's going to have a feedback path and it's going to oscillate. The thing that's going to change what frequency it oscillates at is the varactor, because remember, as the varactor potential or the reverse bias across the varactor increases, its actual capacitance decreases. So you can remember when we talk about resonance frequencies 1 over 2 pi square root LC. So as capacitance decreases, resonant frequency increases. Okay, now let's get into this whole divide by concept. Okay, so then, and then he's going to produce a sine wave, okay, to some extent. That sine wave is going to get produced back here. And if he's not here, it just goes back into here. And if the phase relationships. Now, one thing to remember about these guys is we're never going to get them in phase. What we're looking for is a point where the phase no longer changes. Okay, so if this guy is coming in and then this guy is constantly this relationship, right? So say this guy's ahead a little bit, this guy's behind a little bit. Okay, if the phase relationship is constant and it's not changing anymore, you can say that the two are in phase. In other words, they're hitting the same points at the same time, right? When he's at, say, 0.5 volts, he's always at 2 volts. When that relationship is constant, you can say that we've basically locked on, okay? So the frequency at this point is locked and the output will be just, okay? Now, let's talk about when I want to, in fact, increase my frequency on the output here. Well, this is simple. If I want to increase my frequency, all I got to make sure I do is I divide the output here by some relationship that will increase this potential to return the value back to what I need. In other words, I could kind of fool the comparator to think that I'm putting the same phase relationship of the two signals. In other words, if he's 25 kilohertz, I'm going to put 25 kilohertz here, even though what's actually coming out is something larger. Okay, so say you had let's just start with a 25 kilohertz. So say I want 50 kilohertz. Okay, so you're going to need to divide by 2, right? So if I want 50 kilohertz, I need to make sure that my output is dividing it by 2. So initially, so let's just plug this guy in. It goes through, right? Say he initially put out 25 kilohertz. This signal here will show in at half of 25, which will be, what's that? That's, what is that? 12.5? Sorry. 12.5 kilohertz. It'll show in here. It'll go, this will positive, meaning this range here will go positive. The average goes up. We'll trick him, and this DC voltage will rise higher, triggering the oscillator to, right? So more potential to increase our resonant frequency. Resonant frequency increases. And this is going to continue until these two, the phase relationship no longer changes. When the phase relationship doesn't change anymore, now we have our 50 kilohertz out. A perfect divide by 2 to bring this back to 25 kilohertz. And now we've just tricked the phase comparator into continuously triggering our voltage controlled oscillator to produce 50 kilohertz. And that's essentially how the phase lock loop works. In my next video, we'll talk about how it actually applies in the KY92.